Welcome to the deep dive. Today we're tackling some pretty dense material, really cutting-edge stuff on using reinforcement learning in, well, live cyber operations.
That's right. It's a fascinating area.
And our job, yours and mine, is to sort of act as instructors, pulling out the core insights from this research. For you, the listener, you've put together a great overview, starting from, penetration testing basics right up to these complex AI agent architectures.
Exactly. Think of us as guides through this. We're going to walk through it logically, looking at how AI, specifically this reinforcement learning, or RL, is being shaped to automate and really boost CyberOps.
And that covers both sides of the coin, right? The attacking side, like simulating red team tests.
And the defensive side, helping the blue teams become more effective. It serves both masters, so to speak.
And the why behind all this isn't just academic curiosity, is it? The material makes it pretty clear that the threat landscape is just accelerating.
Yeah. Oh, absolutely. It's almost a mandate now. The core reason. Cyber threats are evolving way faster than human defenders can keep up. Your attack surface is growing constantly. And the adversaries, especially, nation states, they're using machine speed.
Machine speed. That's the key phrase.
It is. And the only real answer, according to this research, is you have to fight fire with fire. Or rather, use AI to combat AI. Machine learning has to become that force multiplier for the defenders.
Giving them capabilities, detection, prediction, response times.
Yeah.
Things humans just can't manage alone or with old rule-based systems.
Precisely. It has to augment human capabilities significantly.
Okay, so here's the plan for you listening. We're going to follow the structure laid out in the sources. We'll start with the basics, the human teams, the processes that these AIs are trying to model.
Then we'll dive into the theory, the math behind it, like Markov decision processes. Don't worry, we'll make it understandable.
Good. And finally, we'll look at the practical side, these large-scale architectures researchers are building to make the math work in real, messy, huge networks. Sound good?
Sounds like a plan. Let's jump in.
Right, let's start where the research does, the human element. Before you can automate something, you need to understand what humans do. So red teams, blue teams, purple teams. Let's define those.
Okay, yeah. These are really the fundamental concepts, the basic vocabulary for any modern cyber testing. Your red teams are the attackers, the offensive specialists.
They're simulating real-world bad guys.
Exactly. Using the same tools, the same TTPs, tactics, techniques, and procedures. Their goal isn't just finding any vulnerability. It's about finding the critical ones, the ones that could really hurt the organization, the ones that maybe traditional scans miss.
Things that put the crown jewels, the really important assets at risk.
Precisely. They focus on those high-impact scenarios.
And then the flip side is the blue team, the defenders.
Right. Their focus is optimization. How do we improve visibility? How do we detect attacks faster and more reliably? How do we strengthen our defenses? They use the intel from the red team.
Like the attack paths that actually worked.
And use that knowledge to actively harden things, plug the holes. It's a continuous improvement cycle.
Which brings us to the purple team. Now, the material makes an interesting distinction here. It's not always a separate team.
That's a key point they emphasize. Often, it's better thought of as a process, a critical collaborative process. Think of it like this. If red and blue are separate ships, purple is the radio communication between them, making sure they're working together.
Why is that process view so important? Why not just have 3 teams?
Because it tackles a common problem. Historically, the red team might finish, write a huge report, and just, throw it over the fence to the blue team.
And the blue team might struggle to understand it or replicate it or know what to fix first.
Exactly. There's friction. The purple process forces them to collaborate. Maybe the blue team watches the red team's attacks in real time. They discuss findings immediately.
So offensive insights get translated into defensive improvements much faster. It tightens that feedback loop.
That's the goal. Accelerate improvement, build resilience faster.
And this whole red teaming thing, it's not just a nice to have for mature organizations, is it? There are often legal or regulatory drivers.
Oh, absolutely. For many industries, it's mandatory. Think finance, healthcare, critical infrastructure. Compliance standards like PCI for payment cards, high PPA for health records, SOX for financial reporting.
They often require demonstrating you're actively testing your defenses against realistic threats.
Right. Red teaming is how you show due diligence. You're actively looking for risks, assessing them, and addressing them. It helps meet those regulations and, maybe more importantly, minimize the damage if a real breach happens. It's really foundational for secure business operations today.
Okay, so once you've got the teams, or the process figured out, the next big decision is the style of the test. And this boils down to how much information you give the red team up front.
And that initial knowledge level dictates a lot, doesn't it? Time, cost, how deep the test goes.
Completely. It's a trade-off. Let's start with the most challenging, black box testing.
This is where the red team gets almost nothing, right? Maybe just the company name or a website URL. Pretty much. Minimal information. The idea is to perfectly mimic an external attacker who knows nothing about the internal workings.
So the red team has to do all that initial digging themselves, reconnaissance, finding out the structure.
Exactly. They spend a lot of time on research, open source intelligence, OSINT, just building that map of the target's cyber terrain.
It sounds slower, more effort intensive.
It is definitely slower. But the upside is you get the most realistic view of what a true outsider can see and exploit quickly. It's an unvarnished look at your perimeter.
Okay, then there's the middle ground, gray box.
Gray box. Here, the team gets a bit more to start with. Maybe some known IP address ranges, email domains, perhaps even basic user credentials.
So it speeds things up. They don't have to spend weeks on basic recon.
Precisely. It lets them bypass some of that initial legwork and jump straight into testing specific areas. Maybe you want to focus on internal network segmentation or test a part of the network that isn't well documented.
It simulates maybe an insider threat or an attacker who's already got a basic foothold.
That's a good way to think about it. It's more targeted, faster than black box.
And finally, white box, also called glass box or clear box testing.
This is the full access mode. The red team gets everything: internal documents, network diagrams, logs, maybe even source code.
Wow. So they know exactly what they're looking at.
Yes. It's the most comprehensive, designed to find potentially every vulnerability, internal or external. Think deep configuration errors, subtle code flaws.
But also the most resource intensive, takes the most time and money.
By far. Most time, most expensive. But here's the connection to our deep dive. The source material highlights that this kind of exhaustive, information-rich white box assessment. Well, that's exactly the sort of thing these advanced AI and RL systems are being designed to accelerate and eventually maybe even automate.
Okay, so if we want an AI to automate these tests, we need to break down the human process into stages, a life cycle. And it all starts with what the material calls the hacker mindset.
Yeah, that fundamental curiosity, wanting to take things apart, figure out how they work, and then how they can be used in ways the creators never intended.
That mindset drives the process. What are the typical phases?
It generally follows a sequence. High level, it's something like reconnaissance or preparation, then scanning, then vulnerability assessment, moving into exploitation, then post-exploitation, which is really reassessing from the new foothold, and finally, reporting.
Let's dig into those first couple of phases. Reconnaissance, that's the passive info gathering, right?
Correct. You're trying to map the target without actually, touching their network directly yet. This includes things like DNS enumeration, mapping IP addresses to domain names, and vice versa. It helps you find all the websites, subdomains, maybe forgotten test servers that belong to the target. It defines the scope of their online presence.
And open source intelligence, OSINT, fits in here too.
Absolutely. Huge part of recon. This is pulling data from public sources. Think LinkedIn profiles for employee names and roles, public databases, maybe configuration files accidentally left open on a web server.
Stuff that seems harmless on its own, but put together
can reveal surprisingly effective attack vectors. It gives the human attacker or our future RL agent those initial clues, potential entry points.
Okay, after passive recon, we move to scanning. This is active. Now we're actually touching the network.
Now you're sending packets, using tools like Nmap, Nessus. You're actively probing IP ranges to find live hosts, identify open ports, figure out what services are running on those ports, and even fingerprint the operating systems. It's building the detailed technical map.
But active scanning creates noise, right?
Right.
It could be detected by the blue team, the Security Operations Center.
Exactly. That's the risk. Which leads to a clever tactic sophisticated teams use, passive scanning alternatives.
How does that work if you're not sending packets?
You leverage data collected by other people who are constantly scanning the entire internet. Think services like Shodan or Census. They crawl the whole IPv4 space continuously, indexing open ports and services.
Ah, so the red team queries their database instead of scanning the target directly.
Precisely. Why is that stealthy? Because the sheer volume of traffic from these big scanners is often dismissed by security tools as just background internet noise. It gets filtered out.
So you hide in plain sight, get valuable intel without leaving your own fingerprints on the target network.
Exactly. It's a great way to minimize your chances of getting caught early on. And this whole process, especially moving towards AI automation, hinges on one critical thing: data. Loads of it. And it needs to be clean and standardized.
The classic ETL challenge: extract, transform, load, making raw, messy security data usable for machines.
It's absolutely fundamental for ML and RL. Let's talk about the raw data itself. Port scanning data is foundational. The scans tell you the state of each port. Is it open, meaning a service is listening?
Or closed. No service there.
Or filtered, which usually means a firewall or some other security device is blocking your probes. You can't tell for sure if it's open or closed behind that filter.
And these states build that map, the cyber terrain. Open ports are potential doors in.
Especially if they're running services on non-standard ports. That's always interesting.
Why? Because custom setups often mean custom mistakes.
You got it. Standard configurations are usually better tested, custom ones. That's where human error in configuration often creeps in. The banner information returns service name, version number that directly feeds into vulnerability assessment.
Okay, so scans give us the map. But a map of open ports isn't enough. We need to know which ones are actually dangerous. That's where vulnerability databases come in, like CVE and CVSS.
Right. CVE, Common Vulnerabilities and Exposures, is like the dictionary. It gives every publicly known vulnerability a unique ID number.
So everyone, red teams, blue teams, AI agents, can talk about the exact same flaw without ambiguity.
Precisely. It standardizes the what. Then CVSS, the Common Vulnerability Scoring System, standardizes the how bad.
It gives each CVE a score, 0 to 10.
Yep. Free, open standard. 10 is critical, easy to exploit. 0 is basically informational. Defenders use this score to prioritize patches. Attackers use it to pick their first targets. It's that initial measure of technical severity.
But we still need to get this data into the machine. You mentioned ETL. The source material talks about output formats from scanners like Nessus XML, CSV.
Yeah, and this highlights a practical challenge. Nessus XML output is really rich, tons of detail about each host. But for AML, data scientists often prefer CSV comma-separated values.
Why? It seems simpler, maybe less informative.
It is simpler, and that's often the point when you're dealing with massive data sets. CSV is incredibly easy to parse, ingest, merge together. If you're scanning thousands or tens of thousands of hosts, you need a format you can easily concatenate and feed into a model.
So for large-scale AI, the simplicity and scalability of CSV often win out over the richness of the XML.
That's often the pragmatic choice, yes. Structure and ease of ingestion become paramount.
Okay, we've set the stage. The human processes, the teams, the crucial role of data. Now let's get into the engine driving the automation, reinforcement learning. And the mathematical foundation here is the Markov decision process, or MDP.
Right. This is a really important abstraction. It lets us move away from tracking incredibly complex histories of everything that's ever happened.
Which would be computationally impossible in a big network.
Exactly. Instead, the MDP focuses on the current situation to make the next decision. It relies on something called the Markov property.
The taxi driver analogy from the material was helpful here. The driver doesn't need to remember every passenger from last year to decide where to go next. They just need to know where they are now, the time, the weather.
That's the essence of it. Formally, the Markov property states that the next state, let's call it cell t plus $1, depends only on the current state and the action just taken. The history before season doesn't matter for predicting the immediate future.
That simplification is huge. So what are the core components of this MDP? The material defines it as a tuple.
Yeah, the basic building blocks are, first, states. These are the descriptions of the situation. In cyber terms, a state could define a specific host. Is it discovered, compromised, firewalled? It captures the relevant aspects of the environment. Second, actions. These are the choices the agent can make from a given state. Think scanning a specific port, attempting a known exploit, trying to escalate privileges. It's the agent's toolkit. Third, transition probabilities. This is the chance of ending up in state tell if you take action on in state S to tell.
Okay, states, actions. But the transition probabilities add a crucial element, right? Uncertainty, stochasticity. Why is that so important for modeling cyber attacks?
Because CyberOps aren't deterministic like chess. An exploit might fail. A firewall rule might kick in sometimes, but not others. A defender might reset a connection. The outcome of an action isn't guaranteed.
So the agent has to learn to deal with probabilities, not certainties.
Exactly. The Polar component allows the MDP to model that inherent randomness and uncertainty of a real network environment. The agent has to learn policies that are robust, even when things don't go exactly as planned.
And the whole point of the agent navigating this MDP is driven by the objective function. What's it trying to achieve?
It's trying to maximize reward over time, specifically the discounted sum of expected future rewards. We often write it as the key part there is discounted.
That's the gamma factor between
Yeah.
0 and 1. What does discounting do?
It makes rewards obtained sooner more valuable than rewards obtained later. A reward received right now is worth more than the same reward received 10 steps in the future.
Like a bird in the hand is worth 2 in the bush.
Pretty much. It encourages the agent to achieve goals efficiently and prioritize immediate gains, which often mirrors how real attackers operate. Securing a foothold now is often better than a complex plan for a payoff way down the line. It adds a layer of realism to the agent's motivation. Hashtag tag 3.2 learnable functions for agents.
Okay, so we have this MDP framework: states, actions, transitions, rewards. Now, how does an RL agent actually learn the best way to behave within that framework? There are 3 main approaches the material outlines.
Right. The first is learning a policy model, often denoted as SAP. This sounds like learning the strategy directly.
It is. The policy model is essentially the agent's guidebook. It learns a direct mapping for any given state, RLers. It tells the agent the best action aller, or a probability distribution over actions, to take to maximize future rewards.
So it learns what to do.
Exactly. Learn the behavior directly. This can be very effective, especially if you have lots of data, but can struggle if the number of possible states is absolutely massive. Okay, the second approach is value-based models. This involves learning functions like value and Q dollars. This sounds less like a guidebook and more like a rating system.
That's a good analogy. Instead of learning what to do, it learns how good things are. The state value function estimates the total expected future reward starting from state sales and following the optimal policy thereafter. It tells you the long-term value of being in a particular state. The action value function, Q, is more specific. It estimates the total expected future reward if you start in state sales, take action, and then follow the optimal policy. It tells you the value of taking a specific action in a specific state.
So Q seems more useful for deciding actions because it rates the action itself.
Often, yes. If you know the Q value for all possible actions in your current state, you just pick the action with the highest Q value. The big challenge, though, especially in cyber, is that the number of states, and especially state action pairs, is astronomical in a real network. You can't possibly calculate and store all those Q values explicitly. Precisely, and that's where deep learning comes in. We use neural networks to approximate these Lavalol or QO functions rather than calculating them exactly.
Makes sense. And the third approach, model-based learning.
This is, in a way, the most ambitious. Instead of just learning a policy or values, the agent tries to learn how the environment itself works. It builds an internal model of the MDP, learning the transition probabilities and reward function.
So it learns the rules of the game.
Effectively, yes. If the agent has a good model, it can essentially simulate or plan internally. It can think, if I take action A, I'll probably end up in state X with reward Y if I take action B. It can explore potential futures without actually having to interact with the real or simulated environment for every single step.
That sounds powerful, but probably computationally expensive to learn that model.
It can be very demanding, yes. But the potential benefit is much better planning and potentially more sample-efficient learning because it can generate its own imagined experiences. Hashtag 3.3 key RL algorithms in cyber context.
Okay, so those learning approaches underpin the specific algorithms that are actually used in practice, especially in complex domains like cybersecurity.
Let's start with one of the most famous ones, Deep Q networks, or DQN. This was a big breakthrough, wasn't it? Combining Q learning with neural networks.
Huge breakthrough. DQN really showed how you could use deep neural networks to successfully approximate those Q values we just talked about, even for high-dimensional inputs like pixels from a video game screen, or in our case, complex network state information.
It makes handling the massive state space of a network feasible. The material mentions the cart pole benchmark.
Right, that's a classic RL testbed balancing a pole on a moving cart. It's simple, but it demonstrates the core idea of learning a policy to maximize cumulative reward over time, which DQN excels at.
And a key component of DQN mentioned is the replay buffer. Why is that so important for making it work? Ah, yes, the replay buffer, or experience replay. It's crucial for stability. See, when an RL agent interacts with an environment, the experiences it collects, state, action, reward, next state, are sequential and highly correlated.
Like what happens now is very similar to what just happened.
Exactly. And feeding highly correlated data sequentially into a neural network can make the training unstable. The network can forget past experiences or get stuck in feedback loops.
So the replay buffer breaks that correlation.
Right. It stores a large history of past experiences. Then, during training, instead of using just the latest experience, it samples a random mini batch of experiences from this buffer. This shuffling breaks the temporal correlations, smooths out the learning process, and makes the training much more stable and robust.
Yeah.
Absolutely essential for complex problems.
Okay, next algorithm. Advantage actor critic, A2C. This one has two parts, an actor and a critic.
Correct. It's a different structure. The actor is responsible for learning the policy, deciding which action to take. The critic is responsible for learning a value function, usually the state value function, estimating how good the current state is.
So they work together. How?
The critic evaluates the state the actor is in, or the action the actor took, and provides feedback. The actor then updates its policy based on the critic's feedback. The advantage part is key here. It uses the advantage function, typically calculated as $1 AV.
Let's break that down. Q is the value of taking action, as the state dollars is the average value of state dollars.
So the advantage is, how much better than average was that specific action?
Exactly. Instead of just knowing if an action led to a good outcome, high Q, the advantage tells you if that action was better than expected for that state.
Why is that helpful? It significantly reduces the variance of the policy updates. Imagine you're in a state where all actions lead to pretty high rewards. Just using Q values might make it hard to differentiate the truly optimal action. The advantage focuses the learning signal on what makes a difference relative to the baseline value of the state. This leads to more stable and often faster learning, especially when rewards are sparse.
Makes sense. And finally, the algorithm that seems to be state-of-the-art in many complex applications, including this cyber research, proximal policy optimization, PPO.
Yes, PPO is often the go-to algorithm these days. It builds on the actor-critic idea, but is known for its superior stability, robustness, and sample efficiency, meaning it often learns well with less interaction with the environment compared to older methods.
How does it achieve that stability, especially compared to A2C?
The core innovation in PPO is how it updates the policy. It uses what's called a clipped surrogate objective function. That's a bit technical, but the intuition is straightforward. It prevents the policy updates from being too large in any single step.
So it doesn't let the actor change its strategy too drastically all at once.
Exactly. A large, sudden change in policy can sometimes lead to a performance collapse. The agent forgets something important it learned previously. PPO puts constraints on how much the policy can change between updates, ensuring a smoother, more monotonic improvement. There's another variant using a KL divergence penalty, but the clipping method is more common.
And that constraint, that careful updating, is what makes it so reliable for really complex, large-scale problems like simulating attacks on enterprise networks.
That's the key takeaway. PPO's stability and reliability make it highly suitable for the kind of challenging environments we see in cybersecurity simulation, where instability could mean the model fails to learn anything useful at all.
Okay, we've got the powerful algorithms DQN, A2C, PPO. We understand the MDP framework. But now, how do we actually connect these abstract mathematical models to the messy reality of a live computer network? This seems like a huge leap. The material calls it the grounding problem.
It is a huge leap, and it's a major focus of the research. You can't just let a learning agent loose on a production network, right? It needs a safe, structured representation to interact with.
So academics often use attack graphs. What are those exactly?
Think of them as maps. They represent the network components, hosts, vulnerabilities, firewalls, and critically, the relationships between them. Specifically, the prerequisites needed to move from one host or privilege level to another via exploits.
So it shows to compromise server B, you first need access to workstation A and need to exploit vulnerability CVE XYZ.
Precisely. It provides that structured connectivity information that the RL agent needs to understand the environment and plan sequences of actions. It turns the network into something the MDP framework can handle.
But the material flag's a big issue here. Generating these attack graphs for real large networks is incredibly difficult, computationally speaking.
Oh, massively. Trying to map out every possible attack path from the start, what we might call a top-down approach, runs into combinatorial explosion. The number of potential states just blows up.
The research mentions complexity, like math callo for simple state enumeration.
Yes. Exponential in the number of hosts. Even more advanced techniques mentioned, like mulval at mathcolo-n2 or netspa at mathcolo-n-login, while better, still become intractable for networks with, say, 50,000 hosts.
So generating the perfect complete map up front is often just not feasible at enterprise scale.
Not really. This computational bottleneck is a major driver for needing more clever abstraction methods and architectures. Hashtag tag 4.2, the layered reference model for RL agent grounding, LRM-RAG-RAG. To tackle this grounding problem and manage the complexity, the researchers propose a specific architecture, a pipeline, the layered reference model for RL agent grounding, or LRM-RAG.
Okay, LRM-RAC. So this is the formal process for bridging the gap, taking real network data and turning it into something the RL agent can actually learn from.
Exactly. It defines the steps. You start with data from the real network. This gets abstracted into an attack graph representation, even if it's incomplete or generated dynamically. That graph structure is then formalized into a generic Markov decision process, MDP.
So far, so good. But the key seems to be the layered part. It doesn't stop at a generic MDP.
Correct. The LRMRG then layers specific context on top of that generic MVP, tailoring it for different simulation needs without having to rebuild everything from scratch. It defines 3 specific MDP layers.
Okay, let's walk through them. First layer, the terrain MDP.
Think of this as adding the physics of the specific network environment to the generic MDP. It models things like firewalls as obstacles with certain traversal costs. Network latency might be modeled as distance. Host properties like operating systems or installed security agents become features of the terrain.
So it grounds the abstract MDP in the specific network structural realities.
Precisely. It defines the landscape the agent has to navigate.
Layer 2, the adversary MDP.
If terrain defines the environment, adversary defines the agent's capabilities within that environment. It tailors the model to simulate a specific type of attacker.
Like, does the agent have access to zero-day exploits or just common ones? How sophisticated are its scanning techniques?
Exactly. It defines the agent's available action set and potentially its inherent risk tolerance or stealthiness based on the profile of the adversary being emulated. You can call script kiddie versus nation state APT.
Okay, so terrain is the map, adversary is the player's abilities. What's the third layer, the task MDP?
The task MDP defines the goal or the objective of the simulation run within the constraints set by the terrain and adversary layers. It does this primarily by shaping the reward function.
So if the overall goal is, say, find a path to the critical database, the task MDP assigns high rewards for actions that move closer to that database.
Precisely. If the task changes to perform reconnaissance without being detected, the task MDP would heavily penalize noisy actions and reward discovering new hosts stealthily. It refines the agent's motivation for a specific mission.
So LRM-RAG provides this structured, layered way to build context-aware MDPs for different cyber simulation scenarios. That seems really powerful.
It provides a necessary formal structure for moving from raw data to actionable RL environments.
Now, having this framework, LRM-RAG-RAG, is great, but research often needs a bigger picture, a North Star goal. The material introduces whole campaign emulation, WCE, as that unifying objective. What is WCE?
WCE is essentially the long-term vision, automating the entire life cycle of a sophisticated cyber attack campaign, from the very first step of reconnaissance through exploitation and lateral movement, all the way to the final goal, often data exfiltration.
So simulating the whole thing end-to-end automatically, that sounds incredibly ambitious.
It is. And the source material acknowledges that current research is often fragmented. You have groups working on scaling RL, others focusing on handling partial information because the agent rarely sees the whole network, others refining the MDP engineering itself.
WCE aims to tie all these threads together, kind of like how whole brain emulation is a grand challenge in AI neuroscience.
That's the analogy they draw, yes. WCE provides a common target for these disparate research efforts. But how do you actually approach such a massive goal?
Break it down.
Exactly. Through modularization, they quote the adage, do not solve a more general problem in order to solve a specific problem.
Meaning, don't try to build one giant AI that does everything at once.
Right. Instead, WCE proposes breaking the campaign into more manageable stages, maybe called G1, G2, G3 in the research. You could have one RL agent specialized in reconnaissance, G1, another focused on exploitation and privilege escalation, G2, and a third handling exfiltration, G3.
So you develop specialized tools for each phase first.
Yes. Tackle the subproblems, develop robust solutions for each stage. Then, the longer-term goal is integrating these modules. They wouldn't necessarily replace human pen testers entirely, but act as incredibly powerful force multipliers, automating large parts of the process and allowing humans to focus on the most strategic aspects.
We keep coming back to the scale issue. Enterprise networks are huge, tens, even hundreds of thousands of hosts. The material has a stark warning here. When RL models scale poorly in cyber, it's not just that they run slow.
It's often much worse. Poor scaling frequently means the model simply fails to converge. It never learns a stable, useful policy. The learning process just diverges or oscillates uselessly.
So the top-down approach of trying to pre-calculate the entire attack graph up front is basically doomed at scale.
Pretty much, yes. It's computationally infeasible, which is why the research strongly advocates for a bottom-up approach.
Mimicking how a human attacker actually works, they don't start with a perfect blueprint.
Exactly. A human attacker, or a bottom-up RL agent, starts with a limited foothold, maybe just one compromised machine or some initial recon data.
Then they scan locally, probe, see what's reachable from there.
Right. They perform an action, observe the result, and then update their internal map of the network, expanding their knowledge incrementally. They operate on partial information, only reasoning about the parts of the network they've actually observed or can infer directly.
This avoids the need to compute the entire state space up front. You only deal with the relevant reachable states as you discover them.
It makes the problem vastly more tractable and scalable. But even with a bottom-up approach, the number of possible actions from any given state can still be enormous. Scan this port, try that exploit, use this tool.
Which led to a key architectural innovation discussed, the double agent architecture, DAA.
Yes, the DAA is clever. It tackles the massive action space problem by decomposing the decision process into two hierarchical levels, managed by two cooperating agents. First, an exploration agent. Its job is high level. It looks at the known parts of the network and decides which host to focus on next. Second, an exploitation agent. Once the host is chosen, this agent takes over the low-level decision. It decides which specific action, from a curated list relevant to that host, to perform. Scan, exploit CVE ABC, escalate privileges.
So it breaks one huge decision, what action do I take on which host, into two smaller, more manageable decisions.
Exactly. And the real power comes when you combine this DAA structure with a stable algorithm like PPO. This gives you DA PPO.
And the results showed a big improvement in stability and speed.
Dramatic improvement. The case study compared DA PPO to an earlier version using A2C, DA A2C. On the same complex network simulation, DA PPO converged to a stable, effective attack policy in just a few minutes.
Whereas DA ATC took much longer.
Took around 30 minutes and likely with more variance. That speed and stability gain comes directly from PPO's constrained policy, updates its ability to learn smoothly, even in these very large, high-variance, partially observable environments typical of cybersecurity. It's crucial for making these techniques practical.
Okay, so we can scale the simulation, but how do we make the agent behave realistically? It's tempting to just tell it, go find the vulnerabilities with the highest CVSS scores. But the research argues strongly against that. Why is relying solely on CVSS scores a bad idea for motivating the RL agent?
Because CVSS only tells you about the technical severity of a vulnerability. How easy is it to exploit? How much access does it grant technically? It completely ignores the business context or the operational importance of the affected system.
The cyber terrain aspect again.
Yes.
Like your example earlier, a critical CVSS 10 flaw on some isolated test server nobody uses. Who cares?
Exactly. Whereas a moderate CVSS 5 flaw on the main authentication server or the primary database, that's potentially catastrophic for the business. A human attacker understands this context intuitively.
So for the RL agent to act realistically, its motivation, its reward function, needs to incorporate that context. We need careful reward engineering.
Precisely. The rewards need to mimic how a real attacker assesses value, which includes considering the inferred defensive posture of a target and its likely impact if compromised.
How did they implement that in the research? It involved negative rewards or penalties?
Yes, they use a clever hierarchy of penalties based on the category of services detected running on a host. This acts as a proxy for importance and likely defenses. Attacking hosts running critical authentication services, like domain controllers, incurred the highest penalty, Manifest 6. Attacking hosts with data services, databases, file shares, got a medium penalty, Manif 4. Attacking hosts with only general security or common services got the lowest penalty, Manif 2.
Interesting. So the agent is actively discouraged from attacking more critical systems unless the potential gain, like finding a high-value exploit, outweighs that penalty.
Correct. It forces the agent to make trade-offs, just like a real attacker. Is it worth triggering potential alerts by attacking that sensitive authentication server, high penalty? Or should I look for an easier, less critical target, low penalty, first?
So a high CVSS flaw on a common web server, not a 2 penalty, might actually be less attractive to the agent than a lower CVSS configuration mistake on a crucial data server, not a 4 penalty, if that data server is a necessary step towards the ultimate goal.
Exactly. This context-aware penalty system pushes the agent towards paths that are not just technically viable, but also strategically valuable and potentially stealthier, mirroring the decision-making of a more sophisticated human attacker. It's about risk versus reward in context. Hashtag 5.3 practical applications of RL and cyber. And with these scalable context-aware models, the research demonstrates applications solving real, practical cybersecurity problems.
First up is Crown Jewels Analysis, CJARL. This sounds like directly mapping to that core red team goal we discussed earlier.
It is. CJARL uses the RL agent to find the most efficient or likely attack paths from various starting points to the organization's designated high-value assets, the crown jewels.
How is that useful for defenders, the blue team?
It gives them highly specific, actionable intelligence. Instead of just knowing protect the database, they see the specific routes the RL agent found to get there. This tells them exactly which intermediate systems need hardening, which vulnerabilities on the path are most critical to patch, and where to focus monitoring.
It highlights choke points and critical dependencies on the path to the jewels.
Precisely, especially hosts involved in active user logins or credential management near the target, those become high-priority defense points.
Okay, next application. Surveillance detection routes, SDR. This focuses on the early stage, reconnaissance.
Yes, SDR tackles the problem of how to explore a network to gain maximum visibility, find valuable targets, while simultaneously minimizing the probability of being detected by the blue team. It's about stealthy information gathering.
And the model for this had an interesting feature, a warm-up phase.
That's right. Before the agent starts seeing it learning, updating its policy weights, it goes through a warm-up period. During this phase, it interacts with the environment, tries actions, observes outcomes like triggering alerts, but it doesn't learn yet.
Why do that? What's the benefit?
It allows the agent to build an initial conservative understanding of the network's risk landscape without reinforcing potentially bad, noisy behaviors early on. It's like a human carefully probing, backing off if they hit a sensor before committing to a strategy. It helps ensure the final learned policy is more risk-aware and stealthy from the start.
That's clever. And the SDR results also showed how simply tuning one parameter of the penalty scale could emulate different types of attackers.
Yes, this was a really neat finding. They varied a global penalty scale multiplier that affected those negative rewards we discussed. With a low penalty scale, for example, scale 1, the agent didn't care much about risk. It behaved like a smash-and-grab attacker, noisy scans, trying lots of things, hitting many systems, leaving a large footprint. Opportunistic, but easily detectable. With a high penalty scale, for example, scale 11, the agent became extremely risk-averse. It simulated a sophisticated APT or nation-state actor taking very direct paths, minimizing interactions, often sticking to a single protocol to blend in, avoiding anything likely to trigger alerts.
So for a blue team analyzing the logs, the Scale 1 agent leaves obvious tracks everywhere, while the Scale 11 agent might leave only very subtle, targeted traces.
Exactly. It demonstrates that sophisticated attackers aren't always noisy. Sometimes the most dangerous ones are the quietest. It highlights the need for detection mechanisms that look for subtle, low and slow patterns, not just loud bangs.
Finally, the research tackled enhanced exfiltration path analysis. This is about modeling the data theft itself after the initial breach.
Right. It's not just about getting in, it's about getting the data out without getting caught. The RL models here learn sophisticated evasion tactics.
Such as?
Things like choosing specific network protocols for transfer, maybe using DNS tunneling or HTTPS, even if slower, because that traffic blends in better with normal network activity than, say, FTP.
Avoiding protocols that stand out to anomaly detection systems.
Exactly. And also managing the timing and volume of the data transfer. The agent learned to incorporate strategic sleep actions, pausing the transfer periodically to break up large data flows and avoid triggering firewall alerts based on connection counts or sustained high bandwidth usage. It's modeling the patient, careful data thief.
So these RL models are becoming quite sophisticated. The next logical step, as the research points out, is moving them beyond just simulation tools and integrating them into day-to-day cybersecurity workflows.
Absolutely. The immediate value is using the output, these predicted attack paths, to supplement human teams.
like a planning assistant for penetration testers, or helping the blue team prioritize which vulnerabilities to patch first based on the RL agent's findings.
Exactly. Instead of dealing with a raw list of thousands of vulnerabilities, you prioritize based on those that lie on the most critical, high-probability attack paths identified by the simulation. It brings strategic focus. It's similar in concept to how tools like Bloodhound are used today to visualize and find attack paths in Active Directory environments, but potentially more dynamic and adaptable through RL.
And there's synergy with other machine learning tasks, too. The RL simulations can help other AI systems.
Yes, a huge potential synergy is between simulation and threat detection. One of the biggest challenges for training modern intrusion detection systems, IDS, especially behavioral ones, is the lack of realistic, diverse, labeled attack data.
Real attack data is hard to come by, especially for novel threats.
Precisely. But these RL agents can generate vast amounts of synthetic attack data, diverse, context-aware, realistic attack paths based on different adversary models. The synthetic data can be used to train behavioral IDS systems much more effectively, teaching them to recognize the patterns of novel or complex attacks they might otherwise miss.
That's a powerful feedback loop. The research also hinted at an even more ambitious future, using RL not just to orchestrate known exploits, but to actually engineer new exploits.
That's the longer-term, more speculative vision. Currently, the RL agents are mostly acting as master strategists, deciding which existing tool or known exploit to use when. The future goal is to develop more granular RL models that operate at a lower level, perhaps analyzing software binaries or network protocols to actually discover new, previously unknown vulnerabilities or even construct novel exploit code automatically.
Wow, that moves from automating the attacker's strategy to automating their R&D.
It's a significant leap, yes, towards agents that can find 0 days, potentially. That's still largely research, but it indicates the direction things could go. Another major area where these models show promise is tackling one of the hardest problems in the field: attribution.
Figuring out who is behind an attack, which group, which nation state. Why is that so notoriously difficult?
Oh, multiple reasons. Attackers use technical means to hide proxies, VPNs, compromised infrastructure. They use false flags, deliberately mimicking the tools or techniques of other groups to mislead investigators. And perhaps most importantly, there's just a fundamental lack of ground truth, labeled data connecting specific observed attack campaigns back to specific known actors with high confidence.
So, again, a data scarcity problem. An RL simulation offers a way to generate relevant synthetic data.
Exactly. If intelligence analysts have some understanding of the typical tactics, techniques, and procedures, TTPs, or even the implicit risk preferences revealed by reward structures of known threat groups, like different APTs, they can configure the RL agent, using the LRM Rago framework, for instance, to specifically emulate that group's behavior.
So you can generate thousands of simulated attack paths that look like they were carried out by APTX and thousands more that look like APTY.
Precisely. You create distinct data sets representing the behavioral fingerprints of different actors.
And then you use this synthetic data to train a classifier. The material mentions techniques like metric learning and triplet loss.
Yes, these are machine learning techniques designed specifically for learning similarity or distance. Metric learning aims to train a model that embeds complex inputs, in this case, entire attack paths into a lower dimensional latent space. Think of it like creating a map where similar attack patterns end up close together and dissimilar ones are far apart.
And triplet loss helps create that map structure.
It's a common way to train such embeddings. For each training example, an anchor attack path from APTX, you also provide a positive example, another path from APTX, and a negative example, a path from a different group, APTY. The loss function then encourages the model to pull the anchor and positive closer together in the latent space while simultaneously pushing the anchor and negative further apart.
So it learns to cluster attacks based on the underlying actor TTPs, even if the specific tools or targets differ slightly.
That's the goal. It learns the style, the behavioral signature.
And the payoff is zero-shot attribution. What does that mean?
It means that if the blue team observes a new, ongoing attack campaign, maybe one they've never seen before, using some novel elements, they can embed the observed sequence of actions, the partial attack path, into this pre-trained latent space.
And see which known APT cluster it falls closest to.
Exactly. The system could say this new activity is 75% similar to the typical patterns of APTX, but only 10% similar to APTY. It provides a probabilistic attribution, even for novel campaigns, based on behavioral similarity to the synthetically generated profiles. It's a huge potential leap for providing defenders with timely intelligence about who might be targeting them. Hashtag 6.3, the AI versus AI arms race, the inescapable future.
Which brings us inevitably to the final section. All these powerful AI tools for defense. Well, the bad guys are using AI too. We're heading into, or maybe we're already in, an AI versus AI arms race.
It seems unavoidable. Malicious actors are certainly leveraging automation and ML. We see it already in automating things like large-scale reconnaissance or vulnerability scanning. But the more concerning trend is the use of generative AI for attack creation,
Like crafting much more convincing phishing emails.
going way beyond that. Think customized deep fake voice calls for phishing, personalized fake video messages, highly targeted spear phishing emails written with perfect grammar and context drawn from OSINT about the victim's job, colleagues, and current projects.
Attacks that bypass simple signature detection and are incredibly difficult for humans to spot because they seem so legitimate and personalized.
Exactly. They target human trust at scale, powered by AI. And beyond using AI to attack humans, there's the risk of attacking the AI systems themselves. The research highlights two main AI attack vectors.
What are they?
First, input attacks, often called adversarial examples. This involves making tiny, often imperceptible changes to the input data, like changing a few pixels in an image or adding subtle noise to audio that trick the AI model into making a wrong prediction or classification.
So fooling the defensive AI.
Right. Second, and potentially more dangerous, are poisoning attacks. This involves corrupting the training data used to build the AI model in the first place. If an attacker can subtly inject malicious data during training, they can potentially create hidden backdoors or induce specific blind spots in the final deployed defensive AI system.
That sounds incredibly hard to detect.
It can be very insidious. Defending AI systems requires not just robust algorithms, but also careful data provenance and validation.
So with attackers using AI and even attacking our defensive AI, what's the long-term strategic response for defenders? The material points to generalization via meta learning.
This is key. Right now, often you train a specific RL model or ML system for one specific network environment, network A. If you move to a different organization, network B, you might have to retrain extensively, maybe even start from scratch. That's too slow for the pace of the threat.
Meta learning aims to fix that.
The goal of meta learning, sometimes called learning to learn, is to train agents that can generalize their knowledge quickly. A meta-learned agent, having been trained on a wide variety of different network environments and tasks, could potentially adapt its strategies and defenses to a brand new, unseen network much, much faster, maybe in hours or days instead of months.
So it learns the underlying principles of cyber defense that apply across different networks, allowing rapid adaptation.
That's the promise. Achieving that level of generalization is critical if defensive AI is going to keep pace with offensive AI in this ongoing arms race. #tag outro.
So we've really journeyed quite far today, haven't we? From the basic definitions of red and blue, teaming right through to these sophisticated multi-agent RL architectures like DAPPO, solving complex practical problems.
Yeah, from human processes to Markov processes and all the way to things like zero-shot attribution. The key theme seems to be this evolution away from simple scoring or top-down analysis towards models that are scalable, context-aware, and focused on realistic operational goals like stealthy surveillance or protecting crown jewels.
That's a great summary. The shift is towards practical utility and realism at scale, driven by necessity.
And what we've tried to distill for you listening is that this isn't just about making existing tools slightly better. It feels like a fundamental shift required by the threat landscape. The models we discussed, they're becoming less like tools for isolated tasks and more like integrated, holistic AI systems capable of complex planning, learning, adaptation, even prediction, driven, as you said, by that escalating AI arms race.
Which leads to a really interesting point the material implicitly raises about cybersecurity as a domain for AI.
You mean its unique nature?
Yeah. It's possibly the one domain where advanced AI exists almost constantly in its natural environment, not just solving a static problem, but interacting dynamically and competitively with other complex software, hardware, and crucially, other AIs.
That's a fascinating perspective, a high-stakes, adversarial, constantly evolving digital ecosystem.
And that brings us to our final provocative thought for you to consider. If we ever see an AI system truly forced by competitive pressure to develop capabilities that significantly surpass human intelligence in a complex, dynamic domain,
Yeah.
Maybe it happens first in cyber defense.
Because the sheer speed and complexity of the threat might compel us as defenders to eventually hand over significant operational control to AI systems.
Exactly. We might be forced to rely on systems that can protect our critical infrastructure effectively, even if their intelligence operates in ways we don't fully understand or find particularly human-like, simply because human limitations become the weakest link against AI-driven attacks.
A future where non-human intelligence is our best defense. It's a compelling and slightly sobering thought. The systems being researched today are definitely the ancestors of whatever that future holds.
Indeed. Well, that's all the time we have for this deep dive. Thank you for joining us.